All right, welcome everyone. Thank you for coming to this plenary session. We are going to start. We're going to focus on Mars. So this is understanding the habitats and searching for life on Mars, latest results, and a look ahead to Mars 2020. The presenters by alphabetical order are Bethany Ehlmann, who is the co-chair with me. I'm Manuel de la Torre, by the way. Jennifer Eigenbrode, over there. We have Barbara Sherwood-Lollar, over there. Don Sumner, Alexis Templeton, and Ken Williford, who is over there. All right, I'll try to be brief. Next slide, or how do I? Is this the one to manage? No. I'm trying to figure out this control. No, that's the pointer. Oh, maybe. Oh, the big button. So, sorry. Some guidelines. Also based a little bit on the dynamics I observed on the plenary session yesterday. So first of all, we're focusing on Mars habitats. There will be a set of introductory presentations of about 5 to 7 minutes. This will be followed by a session with comments and questions from all of you, from the public. And I would just ask everyone, the main speakers as well as to the public, to convey your message, but please keep it brief so that more people can participate. Next slide is about me. What am I doing here? I do work mostly on planetary atmospheres. I'm sort of an outsider to astrobiology, but not completely. So yes, I do work on Mars and on Earth, and right now I'm working with the environmental themes on Curiosity, and in the future I hope to work on Mars 2020 once we successfully land. Why am I here? Why am I interested in this? Is because everyone knows that the environment does have a connection with astrobiology, but we sort of don't talk to each other that much. So I'm looking for those common interests and see how my expertise or others like me can be useful for to your community. So these are probably obvious facts, but as a list of potential connections, we do measure atmospheric composition from the rovers. That is related to signatures, so products of reactions that may be relevant for your analysis and models, and availability of nutrients. We do measure thermodynamic processes near the surface, which tell us the thermal constraints. Do we have the temperature we need? Do we have the water vapor we need? What is the timing? Do we get the radiation levels and temperatures and water vapor we need at the same time? We measure solar radiation on the surface. Someone was mentioning yesterday how relevant that is. We measure on Mars the dust cycle, and as well as the winds, which tell us about transport phenomena, how to transport nutrients or even any biological activity. We measure the global circulation, how does anything spread all over the planet, and as I mentioned earlier, the hydrological cycle. So since these environmental in situ observations that we do inform your models, constrain your models, and may even motivate new approaches or consider new pathways for the processes that you're considering, my question to you will be, what type of environmental investigations do you think you need for your models so that we can provide those? Maybe we do have the instruments, but we haven't thought of the analysis you need, or maybe we don't even have the instruments. So that's what I came here for. And with that, I will just let go to my first speaker, please.
Okay, so I'm Bethany Ehlmann, professor at Caltech and research scientist at JPL, and the other co-chair of this session. As we get my slides up, I want to acknowledge, first of all, Felipe Gomez from the Centro de Astrobiología, who was the other convener of this session but was not able to physically make it. So thank you to Felipe and the members of the organizing committee for the opportunity to tell you about some of the most exciting things that are happening on Mars and talk about why it is so relevant and such a linchpin for understanding habitability of terrestrial planets, possibly including our own Earth. And I'll ask my co-chair Manuel to time me because he may have to pull me off the stage because there's so much to talk about. So I think we're all broadly familiar with the timeline, but I'll just remind you that, and should there be a pointer up here? Folks in the back?
Is the red,
okay.
Is the laser.
And so I'll just remind the folks looking at the timeline here, of course, we're all familiar with the timeline of our Earth and the earliest life that we so far recognize over here around the 3.5 to 3.8 range. Oxygenation, of course, not happening until later. So it is around this time, and it is worth keeping in mind that this is when Mars was at its most habitable. So before the rise of oxygen on Earth is where the action was. This is expressed in terms of geomorphology, in terms of the timing of valley networks and outflow channels, the existence of lakes. And more recently, it's been richly expressed in the mineralogy that we're able to see from orbit and on the ground, clay mineralogy and various salts. If we collectively try to put this into a representation of habitats, I think it looks something like this, that we had subaerial habitats for life lasting until about 2.5 billion years ago, subsurface habitats that perhaps continue on into the present. I say that based on the fact that even some of the meteorites show evidence of alteration. And then subaqueous, underwater habitats that were intermittent. So why intermittent? This is something I think that's really important to keep in mind whenever we consider Mars. And it's fundamentally different from Earth, but it may be typical of terrestrial exoplanets out there. That is, Earth has a moon that stabilizes it. So we go through obliquity cycles where a 1 degree wobble causes massive climate change, glaciation, ice ages. I'm showing for scale here the Mars's obliquity change and the time scale over which it occurs, which is over 500 million of years to 5 million year intervals. And if we consider this, yes, there were habitable environments on Mars, but at the surface, they would have had a periodicity and an intermittency to them. What does that mean for what life does? For some of you, I think that might be great, listening to some of the models where you have to create reactants and then concentrate them. So maybe this is intermittency as a good thing, or maybe it's deleterious because it's hard to adapt. Regardless, though, there are 2 billion years of diverse environments. These include, and this is going to be the quick tour, these include open basin lakes with clays and carbonates. We'll get to explore this amazing delta in Jezero crater with the Mars 2020 rover. So if you like open basin lakes for life, Mars has them. Equally, we have closed basin lakes, and you've heard the results from the Curiosity rover that will be talked about later. Evidence for laminae from lakes that lasted tens of thousands to perhaps up to 1 million years. And then evidence for still later multiple episodes of groundwater coming in and out through those systems, up to about 2.7 billion years based on potassium-argon dating. We've also, in the last few years, and this is work in progress by Ellen Leask, who's a graduate student at Caltech, have been finding an increasing number of these closed basin lakes appear to be connected to volcanic systems. Here's an example where you can see volcanic cones. These are the plumbing of lakes in Terra Serenum. You can see volcanic cones in this lake, and the sediments that are around the corner forming these beautiful stacks are alunite and kaolinite. Alunite is an acid sulfate formed by the disproportionation of sulfuric gases as they reach the surface, presumably in this paleo lake. We also see traditional silica hot springs. I'm showing you examples that we observe from orbit around Nilipotera volcanic cone, these small deposits of silica from springs, as well as the silica that was seen in situ, inferred to be part of fumarolic or hot spring deposits at the Spirit landing site. We see evaporitic playas, chlorides filling basins. We see other basins that are full of thick 500-meter thick sequences of sulfate evaporites from groundwaters flowing in these sediments, so chloride and sediment basins. And then it's perhaps not as photogenic, but we have an amazing exposure of the groundwater plumbing of Mars, exposed by erosion in the form showing ridges of iron magnesium smectite where fluid once flowed, other ridges clearly of different chemical composition because they're made of jarosite, and still other places where there's evidence of carbonate and serpentine. So this is the schematic of what those ridges might have looked like in terms of access to the underground plumbing of Mars. So 2 billion years of diverse ancient paleo habitats. Everywhere that there's a dot on here is a place that I do not have time to talk about. But that's not all. Okay, Mars has gotten, the closer we have looked in the modern time, Mars has gotten more active. There were hints of this seen with the Spirit rover. These are salts buried just this far underground, meaning that they're pretty recent, right? And they're sulfate chemistry. Now, is this because when Mars goes through those obliquity cycles, even 500,000 years ago, liquid water was more stable on the surface than it is today? There's been hints of groundwater. Orsay et al. Have proposed an underground ice pond for some of the radar observations of the South Pole, and others have proposed that these slope streaks on craters could be groundwater. Others have proposed they are not. But is there groundwater on Mars? Finally, and you've all heard the evidence of the recent activity of methane, why does Mars episodically produce methane? There's clearly activity. Is it life? Is it volcanism? Is it hydrothermalism? So I think these questions are extremely important as we look outward with exoplanets and inward in our solar system to understand the habitability of terrestrial planets. I want to leave you, in my 15 seconds remaining, with 3 questions that I want you to consider and maybe come up. Given this 2 billion-year-old rich record in multiple sites, how do we do this as planetary scientists when we have a limited number of missions? How do we know when our search for life, paleo life, is complete on Mars? And would it look different than on Earth? Finally, given this modern Mars activity, how do we determine whether there is life on Mars now? What specific sites do we go to answer that question? Mars is a rich world for astrobiology, and I hope we architect the plan to explore it.
I know, but I don't have my slides.
So if we could have the next slide.
Yeah, I'm not
Sumner.
sure if I have slides or not.
Yeah.
They're beautiful. Okay, excellent. So in spite of the diverse suites of habitats that are potential on Mars, the community has chosen for both Curiosity rover and Mars 2020 to look at lake environments. And this is a lake in Antarctica, Lake Frixell. And even when the external climate is harsh, this is one of the harshest places on Earth, it's still much wetter and warmer than the surface of Mars, we end up with luxuriant ecosystems in these lakes. And a large part of that is because of the duration of liquid water and also the accumulation of resources from the surrounding. So in the Antarctic lakes, I go to study them to understand the microbial communities in large part because there aren't large organisms eating them. And the pinnacles in the lower part here are several centimeters high and represent structures we don't think could possibly form in the absence of life. We have not found those on Mars with the Curiosity rover for sure, but we have found a very long-lived lake. And so those sandstones in the foreground here are delta deposits going from a river system into a lacustrine system. And most of what you see up here, these are dark sand dunes, but we have tens of meters of lacustrine mudstones. And the interpretation of the team is that you have to have had a lake there for a very extended period of time, billions of years ago. And lakes are particularly good because they integrate things from the watershed that feeds into them. The Gale crater had river systems flowing in, and a lot of the minerals that we see are basaltic minerals. We have a lot of amorphous minerals. And as Jen will talk about, we have complex organic matter within these. And one of the nice things about lakes, we've also seen changes, for example, there's some of the deposits that contain high potassium, including some potassium feldspars, there's others that don't. And they're basically taking bits of the landscape around them and integrating them into one place. So by going to a lake, you're both sampling the watershed, and you're also combining materials that are intrinsically in disequilibrium. Life lives on that disequilibrium. Now, one of the unfortunate things is when you observe disequilibrium, it proves that life has not reached its full potential in that habitat. It hasn't actually helped drive things to equilibrium. The Mars 2020 rover is going to Jezero, as Bethany mentioned, and it provides a really outstanding opportunity where we actually have the preserved morphology of the lake basin and the river system in the watershed. Gale Crater, some of us had confidence that there was a lake there once. It's deep and at the equator. But we had no evidence that there were lake deposits before we landed and before we did our field investigations. In this particular case, there's very strong evidence that we had a standing body of water long enough to deposit a significant delta, with this just being the remains of it. Oops, wrong one. There we go. So if life existed on Mars, we have several scenarios about the long-term habitability. This is after Cockle et al., and I really like the idea. So you have sort of the evolution and the proliferation of life that inhabits a wide variety of environments. Yellow here is an inhabited environment. But you can also have areas, even if there is life on Mars, that life was unable to colonize those sorts of environments. So those could be lakes or subsurface areas with liquid water. And so when you're actually looking for evidence of life on Mars and trying to understand it, there's both the habitability and the presence of life if it exists. So there are two scenarios. So say we have life in the subsurface. Maybe it still exists. There are two different scenarios for how it went extinct, if it ever existed. One is that it was unable to persist and colonize from a habitable environment to newly habitable environments. There's a disconnect and an inability to colonize, which can cause extinction. And then there's also the question about whether the habitable environments disappeared. And we don't know whether or not there was ever life on Mars, but when we're looking at these places we can go, it's really important to understand that just because something's habitable and not inhabited doesn't mean there's not life there. And just because something's habitable does not mean that there was actually life there to take advantage of those resources. Yeah. So Mars 2020 will be exploring the toe of this delta that's coming down through here. And one of the amazing things about Mars is a lot of the physics and chemistry are the same, and we end up with amazing landscapes. And whether or not this is inhabited by life or ever was, it's an amazing and inspiring place to explore to actually look for that evidence. Thanks.
Okay, so I want to kind of extrapolate a little bit more on some of the things that have already been said and talk about carbon on Mars. Now, there has been, in the last 4 years, this wave of new observations that have come from the surface of Mars from the Curiosity River. And so if you look up in the upper left-hand side, one of the first observations that came out was about chlorinated molecules, including things like carbon molecules that have up to 4 carbons in a chain, or benzene that has a carbon chlorine attached to it. Now, when we found these molecules, we weren't quite sure what they meant. These are not things that you typically find in natural samples here on Earth. And so it was kind of perplexing. How do we interpret this? What does this really tell us? What's it mean? And our thought was, we're going to move on. You know, maybe we're going to find another treasure trove of molecules somewhere else. And indeed we did. As we moved from the first lake environment at Yellowknife Bay, we moved on to an area called Pahrump Hills, where we came across the Murray Formation. At the base of the Murray Formation, which is shown on the upper right-hand side, we found a whole bunch of other signals in the SAM instrument. This is the Sample Analysis at Mars instrument. And it's a GCMS, but what it does is two different types of analyses, evolved gas analysis and GCMS. It's not, at this point, I don't want to explain exactly what those are, but it's important because it gives us two different insights into what we're coming across, this type of chemistry that's there. And what we found was that when we heated up samples, we actually generated a whole bunch of small little molecules. And those molecules have all different types of chemistry. Some of them are aromatic, meaning they're ring structures. Some of them are hydrocarbon chains. Some of them had sulfur in them. Well, when we put all of those observations together, it tells us that there was a refractory organic material present. This is organic matter. The way we think of organic matter in most natural samples, whether it's on Earth or in a meteorite, these are the types of molecules that we would expect if we had something that was larger than themselves. And when we heat up the samples, they break down into smaller molecules. So I show in the middle there's a little video here, is two molecules, propane and benzene, and essentially what they are little components of something bigger. This is a macromolecule. We found something, we found it, and it makes more sense. Now, the question though is, how does this relate back to the prior observations of the chlorinated hydrocarbons? Well, it ends up that when you take stuff like this and you bombard it with a whole bunch of radiation, particularly in the presence of salts that have chlorine, you actually break it down into smaller and smaller molecules. And they get oxygens attached to them, and they're easy to chlorinate. And so it could be, and this is a hypothesis, it could be that what we're really dealing with is in one place we came across this more refractory complex, large organic materials with sulfur in them, and over time in other places they had broken down into something as simple as the chlorinated hydrocarbons, and that's what's left behind. Well, there's been more observations. It's just not these two. There's a recent observation of hydrocarbon chains, and that's shown in the bottom left-hand side here. And there's carbon chains that have C10 through C12 that might be present. And we're still trying to understand what the significance of this observation is, but for the first time we have individual molecules that are larger than what we have previously seen. So this is another clue of things that are happening, or a record that is still intact somewhere in these rocks. And then of course we have the methane detections that are shown in the bottom right-hand side. And this was a plot that was shown back in 2018. And it shows a fluctuation in the methane signal related to seasons. Now, what's particularly interesting at this point is that the scale bar on this goes up to about 0.7. There was an observation after this, it goes up to about 7 parts per billion methane. But of course, we just had the announcement that there's up to 21 parts per billion. So on this scale, that would be upstairs on the 3rd floor. But there's a lot more to the carbon story. We have evidence from Martian meteorites that there's all sorts of carbon present, and it's been a very labor-intensive process to go through and pick through the little tidbits of organic matter in those Martian meteorites to try and understand what is there. Those are telling us things about Mars, but it's different than these lake environments that we have been studying with the rover. There's also things like interplanetary dust particles raining down onto the surface of Mars constantly. And somehow these can get incorporated into different types of rocks and sediments through the course of processing on the surface. All of this can contribute to our carbon story and the little bits of insight that we get. Now, what I think is particularly interesting is that there was a paper that came out last year in Science Advances by Andrew Steele and co-authors, and it's really kind of pointing to something that we're not used to thinking about here on Earth because it's not prominent here on Earth, or if it is, we don't really see it too much. but I've nicknamed it the Martian Organic Factory, because really what it is basaltic minerals, salts, and brines working together to basically cause a geochemical corrosion that is it's a battery, and it's stimulating electrochemistry. And as a result of that electrochemistry, it can actually produce organic molecules. It takes CO2 and reduces it. So perhaps some of these organic molecules that we're picking up, maybe they're coming from interplanetary dust particles. Maybe they're coming from this Martian organic geochemical factory of producing organics. Maybe they're coming from some, ancient form of life. We don't really know. That's a big question. Yep. So the point I want to take away from this is that we have a new set of observations, and our perspective of carbon in general on Mars has changed. And what was a seemingly stagnant place maybe is actually active. We have a carbon cycle. And right now, we need to start working towards understanding not just sources, but also the processes that are influencing how that carbon moves around the planet as a system.
Thank you. So, move forward, pointer, and clock.
Okay, sounds good. Thank you. So I'm Alexis Templeton from the University of Colorado and the Rock-Powered Life NASA Astrobiology Institute. And I was asked to actually take us back to Earth a little bit, but to talk about some of our recent exploration looking for extant life and fossilized life in hard rock systems, and where we've been looking at rocks that have undergone at least partial hydration and often carbonation, and how do you try and detect life activity, again, that might have relevance for Mars. And the environment that I want to just take a few moments to put into your mind today is one here where on Earth we can often have uplifted sections of mantle rock or peridotite, ultramafic rocks that have undergone prior water-rock interaction histories, oftentimes on the seafloor, or an earlier history of their behavior. And now they're sitting, in this case in Oman, in a desert environment, highly arid, and a low level of hydrological activity in terms of both recharge and discharge from these systems. What's incredible, though, when we go and we start probing into the subsurface in these environments is that actually the storativity of water is enormous. So it's a giant aquifer through kilometers of depth and both laterally that's storing water and under conditions that are surprising and at a limit for where we could look for potential life activity. And then we have bleed outs of fluids that have been stored for long periods of time, long fracture systems and faults that delivers both biota and gases that have been produced over long time periods in the subsurface. So in particular, methane is one of the products that we see. And the idea, again, is to remember or imagine that these rocks are being held often at low temperatures. So we're well under 50 degrees C, and sometimes at just a surface temperature. We're not cold, but there's nothing hydrothermal occurring here. We've been drilling into the deep subsurface, usually over hundreds of meters. We have about a kilometer of continuous core now at this point in time where we're searching for the distribution of life activity. And one of the notable things, even as we're drilling, is that you only have to go meters into the subsurface on Earth with an oxic atmosphere to scrub out almost all signs of molecular oxygen. So in this case, we're sitting with atmosphere that's been percolating into these rocks over 80 million years. Over 20 meters, we've already removed all oxygen from fluids, and you move in the rock system into highly anoxic, iron-2 rich rocks that are buffering the aqueous geochemistry and the conditions under which life's functioning. And we can probe this for microbial activity into a series of different regimes. The majority of our focus is typically on areas where there's large chemical disequilibria. It's often a guidepost for the ways we try and hunt for life activity in subsurface systems. So for example, we can often look at areas in midpoint redox potentials and pH, and we have no question there in terms of looking at quite diverse and functionally active communities. My goal today is actually to take you to a much more extreme condition, but one that I think might be very important and relevant for Mars, which would be coming to the sort of lowest redox potentials, being poised on the stability limit of water. We can hold water under that condition for a very long period of time, and we see biological activity under those states. The issue in these is not whether there's hydrogen or carbon or energy sources, electron donors for growth, it's getting oxidants and then the carbon needed to synthesize biomass. And if you don't have fluid circulation, if you're not hydrothermally active or having a large amount of convection, how do you continue to function? That's the enigma. So what we're trying to refine at the moment are our strategies. How do we go through, again, many cubic kilometers of rock, hunting for the interfaces and where life is localized that's able to continue to persist and function under these kinds of aqueous geochemical conditions and in the rock-hosted environment? And two of the metabolisms we're tracing the most intensively at the moment have been methanogenesis and sulfate reduction, both of which we can demonstrate happening within the rock matrix at depth. And today and tomorrow I'll give a talk that will sort of speak more holistically about our findings. At the moment, again, I'm just staying on the methane theme. What's been exciting is if we can go down and extract methane out of these environments and try to identify its origin and source, almost every geochemical and biological parameter that we measure indicates that it's biological in origin. So we're sitting again in these low temperature conditions. Stable isotope geochemistry has not been very useful to us. This is a really carbon-enriched system. But isotopolog parameters and looking at kinetic bond disorder in the methane have been very instructive in terms of telling us something about biological production of methane. Emily Krauss on Tuesday gave an excellent talk where what she's been looking at is the remarkable abundance of methanogens that are present in DNA extracted out of these subsurface fluids and being able to show transcription and activity in those same samples that's dominated by methanogenic organisms. Another paper just published this year by Libby Phones also was probing the distribution of methanogenic activity across a diversity of chemical regimes we see in the subsurface, and looking at the 14 carbon incorporation into methane through CO2 reduction and into biomass, because again show that even when we go to high pH conditions and low CO2 availability, that we're able to see methane production proceeding. The question is how? And we need to understand a lot more about the physiology of organisms that really inhabit some of these environments, especially when carbon's not available to them, and yet they're still able to slowly pump out methane. We've been fortunate in part of the work in RPL that we were able to isolate this dominant methanogen we're finding broadly distributed on Earth in these continental peridotite-hosted aquifers. So this is a methanobacterium species that's being detected in all sorts of studies that are being published at the moment. And typically, we study it under something that's more moderate in terms of the alcohol availability. Following on work, that, for example, that Tim Krall had done looking at carbonate minerals as a potential way to do methanogenesis on Mars, we've been pushing sealed. And even when you're above pH 10, there are, again, physiological mechanisms rocks and use that CO2 to produce methane at very slow rates, but persistent rates, and with a biological signature that's in it. Okay. And last slide of sort of conceptual data would be that what's been promising is that there's a lot of indicators from recent studies too that when you go into these carbonated hard rock systems, the preservation potential for the both extant and fossil microbial communities is really high. So it's helping us to again to develop the search strategy of where to look for these organisms. So the key idea that I want to relate and translate back to thinking about where we're going to look, or where you should be looking for this kind of slow methanogenic activity in a hard rock system on Mars, is that we really are able to not only go into actively circulating groundwater systems, but we can move to static ones so long as the rock was previously carbonated early in its history. And we can have persistent methane production, storage, and subsequent release in these long residence times fluids. And I think that's really promising for starting to consider some of the interactions between the subsurface and the shallow surface environment. Thanks.
Thank you. I'm Barbara Sherwood-Lollar from the University of Toronto, and as soon as the slides come up, you'll note that I have skipped the title slide because in some ways, what I'm about to do is kind of a continuation of the beautiful setup that Alexis did in terms of these terrestrial analogs. But in our case, I'm going to take us back in time and deeper in depth, and particularly focusing on some of the information that's relevant to Mars and other astrobiology targets related to the Precambrian rocks of the planet. Mars isn't the only planet that we need to go to take a look at ancient rock. Sometimes it flies under the radar a bit, unless you happen to be Canadian and live on these rocks, or Australian, but 72% of the continental crust by surface area is Precambrian in age. Now, of course, it's not as old, there's not as much that's preserved as old as Mars, but nonetheless, of that 72%, 14% is Archean in age, mostly between 2.7 and 3 billion years. That's a lot of real estate. And the beauty of it is it allows us to take a look on this planet at analog systems that can give us information about these kinds of organic factories that Jen referred to, and the kinds of processes and balance between microbiology in places where we see active microbial populations and other places where we see, in fact, dominance of more abiotically driven organic synthesis in the deep subsurface. So really that's what I'll be focusing on here, is a little bit talking about why it is these deep fracture systems that we investigate right from surface on down to 3 and 4 kilometers, why they're particularly important as we think about the exploration of habitability and potential biosignatures for Mars. These are fracture-controlled systems. They sustain habitability and energy gradients. They're very hydrogen-rich, on the order of millimoles, and methane-rich, and they also contain abundant organics such as ethane, propane, and some of the small molecular weight volatile fatty acids like acetate and lactate. One of the other important reasons to take a look at these systems is that because the major periods of ultramafic production on our planet were in the Archean, if we're particularly interested in some of the processes that Alexis was pointing out around the production of hydrogen and electron donors and acceptors related to serpentinization and ultramafic rock, that it behooves us to take a look at these. These are the largest exposures of billion-year-old ultramafic rock on the entire planet, and with direct relevance then to the investigation of these processes for Mars. As Alexis mentioned, these are low-temperature systems. Within these systems, we see typically less than 100 degrees Celsius, and yet abundant production of hydrogen via radiolysis and serpentinization, depending on where we are. And as I mentioned, abiotic organic synthesis as well. The key, or one of the key reasons to take a look at these systems in addition to other Earth analogs, is because they do allow us that capacity to not only look at active reactions, because indeed, as Jen pointed out, these are places where the carbon cycle and reactions are still taking place. But nonetheless, because of the very low temperatures, these are more sluggish rates of reaction. So we have both reactivity, but also preservation in the subsurface. And in particular, because they are deep, because they are in fractures, in some of these fluids we see preservation of the products of processes that may have been going on for millions or even billions of years. Another advantage of these is as we get deeper, it allows us to take a look at another spectrum of sites, particularly down below 2 and 3 kilometers. We have a handful of sites where we do see life, but it seems to be life that's present within systems that are still primarily dominated by abiotic processes. So it provides us another step further on that spectrum that Alexis laid out, an ability to look at subsurface processes where there's abundant methanogenesis and sulfate reduction going on, all the way down to systems in which microbiology may still be there, but it's just turning over very, very slowly in a system that's still dominated by abiotic reactions. And in that case, might once again be something that might be a closer analog to the types of things we'd be looking at on Mars, where if there was any life or is any life, it may be a tiny baseline blip up over a largely abiotic baseline. And then finally, of course, because the plates of our planet, the cratons, are tectonically quiescent, they provide us with also an analogy to take a look at something more similar to a single plate planet like Mars, where preservation of fluids and potentially biosignatures may take place on planetary timescales. These are some of the papers that you can take a look at if you're not familiar with this work and want to take a look at the details. Again, one of the key things is the findings from this has been an understanding that there are habitable environments 2, 3, 4 kilometers down in billion-year-old rock, where the products of those reactions and the products of those, in some cases, microbial population of those systems are preserved on global and geologic timescales. But with the renewed interest on methane on Mars, I thought I'd take a couple of moments to just point out some of the key connections to that finding. And because one of the questions I often get asked is, why do we care about something that's happening 2 kilometers down? What's the relevance of that to the surface of Earth, let alone the surface of Mars? So one of the things that's important to emphasize is that there are indeed conduits to the surface for these systems. We typically do go down to take a look at them, but there are many other places where we can look at them from the surface. There are places where diffuse gas over the cratons is being released. This is from an ultramafic rock in northern Ontario that's only about 2 to 3 meters below surface in a small boring we put into an ultramafic rock. And what you're seeing there is the discharge of something that's about 30% hydrogen and 60% methane, very much within reach of the surface. I think Jen referred to the fact that in some cases that redox transition happens more quickly than we expect. And then these are pictures of some of the perennial springs in the high Arctic, where once again, fracture-controlled movement of groundwater coming through the permafrost on a permanent basis shows us that some of these subsurface processes indeed can come to the atmosphere. I'll just close then just by reminding people in the context of some of this work of the astrobiology strategy that was done last year. Rather than talk just about our own work, I wanted to place some of the things I've just said in the context of that strategy. There were a number of key take-home messages within the strategy, one of them referring to this idea of reminding us all to go broad when we think about the investigation of life. And so I think what we've seen today across the board in the panel's talks is something that reflects that. Indeed, a focus on the idea that as we look at biomarkers or signs of past life, we want to definitely focus on rock types where electron donors and electron acceptors may have supported or continue to support chemolithotrophic life. And thinking about the kinds of biomarkers that might tell us something about rock-hosted life is clearly an important part of that strategy. And then finally, just to wrap up with my very last slide, the key issue as well, one of the main take-home messages of that report was the idea of going deep, talking about the necessity of understanding subsurface processes and subsurface environments for life. And indeed, the report made, I think, a couple of important points that drilling technology is, of course, extremely important, the ExoMars and other drilling development, but also indicating that, of course, as we've seen reflected here today, understanding the subsurface can in fact involve a wide variety of investigations in addition to drilling. Geophysical methods such as probes, the InSight lander, for instance, the investigation of geomorphological features, and just to end where Manuel started us, this idea that subsurface processes impact atmospheres. And so that, in fact, that conversation that's developing between astrobiology and subsurface scientists and those who investigate the atmospheres is going to be important not only for understanding Mars, but understanding the search for life.
Great. Well, good morning, everyone. I'm Ken Williford from the Jet Propulsion Laboratory. I'm an organic and isotope geochemist, and I'm also the deputy project scientist for the Mars 2020 Rover mission. Bethany, when she asked me to be part of this panel, suggested I say something about lessons from early Earth and Mars 2020. I've stuck Mars sample return in there because, in part, that's the lesson from early Earth, which we'll get to in a moment. But just to begin with a few lessons from early Earth, these are not self-evident truths. These are lessons that I take personally from early Earth, but I think they're valid. Actually, before we get to that one, I just want to point out what you're looking at here. You're seeing a slide of I'll go back so we're not confused by the lesson. So you're seeing a microscope slide sitting on a microscope with transmitted light going through it. And this is a sample of the Gunflint Formation, about 2 billion years old, 1.9 billion years old. And there's an arrow there pointing to a filament that you can tell once it comes into focus. It has a sense of being hollow. It's brown. The brown is organic matter, a type of organic matter that Jen talked about. This is kerogen, it's a 2 billion year old kerogen, organized into what is, I would call, a very biologically suggestive morphology, but it's a very simple morphology, right? It's a simple tube, but it does, look like an organism. And then around that filament, you see lots of other little blebs and blobs of kerogen organized into different shapes that are variably informative or not. Some of them we think are probably broken up little bits of organic matter. Some of them, there's one up by the N in lessons. If you watch that come into focus in a second here, it's a little blob with tiny little subfilaments coming off of it. So that is potentially a different kind of organism. Anyway, this is in some cases some of the best examples, the most obvious examples of Precambrian life on Earth, and in fact, this example is one of the first examples of Precambrian life on Earth to ever be discovered back in the 1950s. So what are the lessons? Signs of any ancient Mars life are likely to be small, rare, and cryptic. Okay, so life on ancient Mars, we believe, was completely microbial. Without free oxygen, you don't get very large as an organism. And so you're likely to be small, like this, sort of micron scale. But there are exceptions. So these small things can organize into communities, into microbial mats that can get large and macroscopic, things like stromatolites. And we may indeed expect to find things like stromatolites, but these things on early Earth are rare. They exist, but they're rare. And the rarity of signs of life depends in part on what type of habitat we're looking at. We've heard about lots of different types of habitats. Biosignatures are more or less rare in different kinds of habitats, and then they're cryptic. They're not only hard to find, but they can be very difficult to understand and very difficult to gain confidence, for us to gain confidence that they are indeed biological. Context is absolutely critical. So that's what we're working on with Mars 2020, is to establish that context. So the second lesson here, based on all of that, satisfactory confirmation of biogenicity, that is our ability as a scientific community to conclude confidently that evidence we've found in old rocks on Mars clearly came from life on Mars, will likely require the most powerful analytical techniques available on Earth. So this leads us to the second point, which is Mars sample return. So in preparing for a conference on Mars sample return last year, I went digging around the JPL archives to try to find the oldest reference, sort of official reference to Mars sample return in the JPL archives, and came up with this with my friend Mickey, the JPL librarian, dug this out for me. From 1984, a study on Mars sample return, where the architecture is shown pretty obviously here. You have a little rover. You need something to go out and get samples way before a Mars rover ever actually existed. It has a few scientific instruments, some communication capability there, and then you have a lander, and the lander has a rocket on it. In the rocket, near the top, you see a sphere. I think that sphere is probably what we now call the orbiting sample, because that rocket launches the samples collected by the rover into orbit, and there in the top of the image you see an orbiter, which does communications for the other missions, but also rendezvous with those samples, and eventually brings them back to Earth. So here we are 35 years after this, and we're in the wrap-up stage of a study jointly between NASA and ESA to put together an architecture for Mars sample return that would be a cooperative effort, campaign of 3 missions, two additional missions beyond Mars 2020. It's not official yet, but it takes a lot of, as you can see, a lot of persistence. This idea has been around for a long time. A lot of persistence, a lot of patience, a lot of, probably cooperation and compromise to get this done in a partnership between these 2 big space agencies. So let's hope for the best for that. But right now, we're at, we're putting together Mars 2020, the first part of that. And it's really starting to look like a rover in the big clean room at JPL, the spacecraft assembly facility. This is a recent picture from, let's say, a couple weeks ago. We have wheels now. We have a mast. You can see the wind sensors from Meta are on there on the mast. And the arm was recently installed. So there's a webcam where you can watch this live. If you haven't seen this yet and you're interested in this sort of thing, Google JPL Mars 2020 webcam, and you'll find a live image of the clean room and see lots of images like this of them putting it together. But just to very rapidly get through this, I know I'm running out of time here. We've got these 4 objectives. We're going to land on Mars, do basic geology, try to understand how did these rocks form and how were they altered. We'll assess whether the environment of deposition of these rocks was habitable, and then take the next step and actually directly search for signs of ancient life. As we do that, we'll select locations that we think offer the best potential to preserve not only signs of ancient life, but Mars sample return is much bigger than astrobiology. Astrobiology is a very exciting motivation for sample return, but we really want to understand how the planet Mars evolved as a broader system. So signs of planetary evolution as well. And then everything we do with an eye toward enabling future human and robotic exploration. We have this payload. I won't go through this, but check out our website for all of our fantastic capabilities we have. We have new engineering cameras. We'll be taking color images with our engineering cameras, stereo zoom cameras on Mastcam Z. We've got a ground-penetrating radar looking beneath the surface of Mars for the first time from the surface of Mars. And then an advanced instrument for remote geochemistry, remote spectroscopy up on the mast in SuperCam. And then Pixel and Sherlock, which are two instruments out on the turret, which are mapping instruments. And the selection of these instruments, I believe, follows on a community trend in the search for the most ancient evidence for life on Earth, and a reliance on spatially resolved analysis and mapping instruments to find these small, rare biosignatures and understand them given their cryptic context. And so Pixel will map the elemental composition at a scale of 100 microns over a couple square centimeters, and Sherlock is a deep UV Raman and fluorescence mapper with a capability to detect and classify organic molecules. So the last thing I'll say here is to give you a little bit of a zoomed out image of our landing area. So this is Jezero Crater you see here, but put in its regional context. And if you were paying attention over the last several years, we had this incredible 4-year conversation, and a bunch of the people on this stage and others in this room were leaders and participants in that conversation, where we evaluated these different possible habitats on Mars. And it really came down at the end to, I would say, these top two as the leaders and kind of the end members of this surface versus subsurface debate. And I think it's led us to a mission concept that is much richer than it otherwise would have been, where we have, so starting with Northeast Syrtis down to the south there, Jezero Crater up to the north, we have this new ellipse called Midway. We asked the question, how close to the Jezero Crater site could you push a safe landing ellipse where a mission like Mars 2020, a follow-on mission for sample return, could land safely given Mars 2020 landing capabilities? How close could you push it to Jezero Crater and still access the kinds of subsurface habitats that we were talking about with Northeast Syrtis? And so that's the Midway ellipse. And so this is our mission concept. We begin in Jezero Crater, exploring and sampling a clearly habitable surface habitat there, a crater lake. But then we step outside the box, as Barb mentioned, if the box is the crater lake, and we investigate the crater rim, possible impact-generated hydrothermal systems, and then the terrain outside, where we have aqueously altered, potentially ultramafic rocks and diverse subsurface habitats. So that's where we're going with 2020 and what we're looking at for Mars sample return. Thank you.
All right, thank you to all the presenters. I let Ken go over time because he was essentially the one that was focusing more on Mars 2020, which is part of the main goal of the discussion as well. Also because we have about 20 minutes left for questions or comments. That should allow possibly for at least 4 or 5, at least, depending on how long the questions are. So please go ahead.
Hi, I'm Mike Wong from the University of Washington. Thanks to the panel for a wonderful discussion. So we've heard a lot about our amazing flagship rovers, robotic geologists on Mars, robotic astrobiologists soon. And I'm wondering, because a couple of friends and I have been contemplating a sort of orthogonal approach to Mars planetary science, where in addition to sending our big multi-billion-dollar rovers, we send a lot of small, like single experiment, almost disposable, kind of CubeSat-like landers to Mars to sort of get a global coverage of maybe just one specific property. So for instance, I'm an atmospheric scientist. I would really love to know the trace gas distribution at the surface of Mars, all around Mars's globe. I can imagine that geologists would also be very interested in sending a lot of small drills to sort of assess the redox state of the near subsurface of Mars all around the globe. And I was just wondering if the panel thinks that this is something that is worth pursuing in the Mars program, or maybe there are even plans to do something like this.
So I can take the answer, or do you want to take it?
I think everyone can give a very short answer.
So,
or everyone who wants to.
The answer is yeah, there are initiatives, there are lots of studies going on, and there are actual NASA calls for proposals, announcements of opportunities that do enable those kinds of proposals. Any other one?
I would say that I think we're at a really exciting juncture in the Mars program where we're about to accomplish, we think, the goal of the last 35 years, but there's also something fundamental changing, which is this architecture enabled by small sats in terms of the ability to access the surface. And I think that dovetails very nicely with the diversity of Mars that we've discovered, the diversity of questions about the ancient record and then questions about the modern record. So I hope that we can have a program in parallel that includes some of these smaller, less expensive missions of opportunities to figure out, yeah, are these trace gases signs of biological methane? Can we land at some other habitats and or potential habitats and scout them out for future life-focused missions?
I also agree that more observations in diverse places are interesting and important. One of the things for the small satellites or small missions to consider is actually the operations. So running a mission is like a whole nother ball game. And so one of the key things is not just to think about what you want to send and what you want to measure, but how are you actually going to be able to use that? We need data downlink, for example. We need an infrastructure for operations and not just sending the small missions.
I like the idea, but it's awfully big. I think that the potential for using multiple spacecraft assets on the ground in a way to network them together to achieve a different type of science that's more of a regional basis, maybe not global in nature, but regional, is possible in our future. And I think that autonomy is going to be pretty important to making that happen. So I think you're on the right path, but I would suggest you scale back a little bit.
Yeah, I'll keep it quick. So I love this idea, actually, personally. It's a future vision for Mars exploration that I really like. I think after Mars sample return, I think we're likely to see a continued focus on the push to get humans to Mars. That's likely to consume a lot of our energy and resources. But I would love to see a program that works on mapping Mars at a much higher spatial resolution than we currently have from orbit. And there are a lot of different concepts for doing that, but it's a great next step, I think.
So, yeah. Next, please.
Charles Cockell, University of Edinburgh. I was wondering whether the panel could say something about the value of a lifeless Mars. I mean, clearly it's difficult to show there was no life on Mars. But if we looked in those paleo habitats that Bethany showed, and we didn't find any evidence of life, what would be the value of those? Could they be useful for control environments, for example, for understanding geochemistry of early Earth without life? And also, I think it would be deleterious to convince the public that the lack of a discovery of life was somehow some sort of disappointment for astrobiology. So my question for the panel is, Mars red and dead, then what?
So I think there's a lot of comments from the panel that may come forward. I think there's an incredible amount of interest in what kinds of prebiotic organics may have been delivered or preserved. So Jen started to speak about this. Even in the systems that I was discussing today, where we're looking at these mafic and ultramafic rocks undergoing hydration, there's a series and cascade of carbon reduction reactions that have been both hypothesized, and now we're getting better at detecting them in rocks recovered from the subsurface on Earth. They are overprinted by biology. If Mars is lifeless and we can see the distribution and the spatial arrangement of how they're localized and the processes that form them, and that's preserved, that would be incredibly useful information as well.
Lack of evidence of life for all these missions would not be evidence for no life on Mars. That's a really hard one to rule out. However, the best that we could do is go to places where we think is the best place for us to find it. Just tapping into everything we know about astrobiology here on Earth today and how we relate it back to Mars. And so if we go and we look and we don't find what we think should be there, if there is life, then perhaps we just didn't go to the right place. Perhaps life is something different there than what we expected, and we just didn't look. We didn't use the right tools to find it. There will still be unknowns. However, because we're sending humans to Mars, there's also potential that we're going to be putting life there. I know that planetary protection aims to keep it rather clean and protect it. But honestly, if you put a human on the surface, human is life. We will be putting life on Mars, no matter what. And so things might change on Mars. So I think it's almost in generations of lifetimes here, we may be looking at the beginning of a grand experiment when we put humans on Mars and what it means for astrobiology.
I'll just say, Charles, that I love your idea actually of uninhabited habitats, and I think it's a really important consideration for astrobiology because going back, the Drake equation, is like classic, right? Like how many but the key parameter is right. How many if there are habitats in the universe, what fraction of them are inhabited? I agree, it's hard to prove a negative for Mars, which is why I think the key question is how do we explore it, and how do we explore it comprehensively, taking into account diversity, taking into account that we maybe want to look for modern life before sending humans, or do so in a intelligent way. So these are key questions that this community will grapple with as we move forward.
Right. Thank you. So next, please.
Marie-Paul Basset, Strasbourg, France. I have one remark and two questions for Dr. Alexis Templeton talk. The first remark is that in the chemistry laboratory, there is a reaction which is well known and which is never mentioned, never presented in astrobiology. It is the fact that NaHCO3, which is called sodium bicarbonate, decomposes at 50 degrees Celsius and entirely at 270 degrees Celsius to form CO. And I think it should be considered in astrobiology in planetary systems. Then I have two questions. You showed a lake at the start, and I misunderstood the name, so I would like to have the name. And second, I like to know the length of the core that you presented.
Excellent. So, one, thank you for your comment about the bicarbonate decomposition. And carbon monoxide itself is incredibly important right now for understanding its formation and reactivity even at low temperatures. In the pictures that I was showing in those images, what I was showing was in the Ehlmann ophiolite, where we have a massive exposure of ultramafic rocks. The moment we have a series of areas that are drilled approximately 300 to 400 meters, it depends on the holes, with excellent core recovery. So we have 100% core out of all of the places that we've pulled those out from about a year ago. So those are the ones we're now doing intensive life detection and assessment on. And the water that you saw emerging out of a subsurface environment there is from the Kafifa spring, which has been well studied geochemically. Everett Schock's lab and some of his students here, James Leong and Alta Howells, have been actually looking quite a bit at the microbial communities there in those discharge fluids coming to the surface as well. So that's one of the environments. But these places where bleed out of subsurface fluids occurs, it's been stored for very long periods of time in the subsurface, are quite common.
Thank you.
So, thank you. So next, no? Okay, so next question, please.
Dirk Schulze-Marco from the Technical University Berlin. So my questions probably go a little bit further back. Pertains to the Mars sample return. So from the Viking mission, one thing learned there is if you put something in the box, so whatever you measured, the chemical reactivity or the biology was gone after a while. So my question is the following. So when you go to with the Mars 2020, if you sample something in the cache, what is the selection mechanism? How do you decide what sample you take? And is there anything that you measure before you put it in the box, what it is actually, what you put in the box? Is there any kind of in situ measurement? And if not, why not?
I think we should let Ken answer that with his project scientist hat on, although I'll be happy to chime in.
Sure. Okay, so first of all, I want to mention that Mars 2020's objectives and the objectives of Mars sample return, to the extent that they currently exist, the current vision for Mars sample return is focused on ancient life. And so it's certainly true that if we're successful in bringing samples back, people will be interested in looking for evidence of extant life in those samples, but our focus is on understanding whether or not there's evidence for ancient life on Mars. So there's very different concerns in terms of what you alluded to with putting things in a box and the signs are there and then they're not there. Now, you specifically asked, how do we choose the samples? I don't have near enough time to talk about that, but that is what I kind of spend 100% of my time thinking about with the science team. Is we're developing that plan right now, and we have been for years, and it's ramping up. We're focusing on our strategic planning right now for, I showed you where we're planning to go, so we have that level of plan, but it gets much more detailed than that. So we're mapping the landing site now, and we'll select regions of interest. We'll choose campaigns within those regions of interest, and we'll explore that territory using a model that looks similar to MSL, but where the exploration is really focused on guiding us toward the selection of those samples. We will be making many in situ measurements before we choose a sample. They sort of culminate in these mapping instruments where we deploy the arm and we'll abrade a target. We have an abrading bit on the drill, so we'll abrade about a 4.5 centimeter circle and flatten that rock surface, and then we'll deploy the pixel instrument to make an elemental map over a couple square centimeters with a beam size of 100 microns, and we'll make a spatially co-registered Sherlock map where we're mapping with a Raman spectrometer to potentially detect organic matter, but also get mineralogy at that same scale. And that'll, of course, be taken together with visible light images with the Watson imager. And so that's our sort of richest data set. All that obviously is supported by the remote science instruments, but that's our richest data set to tell us what we likely have sampled. We probably will not sample exactly what we mapped, but something as close as possible to that, where we have good reason to believe that our sample, the data we've taken, are representative of the sample that's in the tube. What we will not be doing is making any measurement on the sample itself that we've collected after we've sampled it. So once we decide drill here, the next thing we know is we have data down that says you drilled it, it's in the tube, it's sealed up. We should have one picture of the top of that sample taken from inside the rover, but that's it until the sample comes back to Earth, when we can deploy all of our
we have about 5 minutes left,
yeah.
So we, the panelists, have to also try to be brief. We have 5 people. Let's see how far can we get. Yeah, please go ahead.
I'd like to start with Barbara Sherwood-Lollar and end with Don Sumner, and the other panelists can situate themselves in between in answering this question. And maybe each of the panelists could say how to sample the atmosphere, according to include that in their answer. If there was some carbon shown on the Mars 2020 sample shot, and assuming that there's been some subalteration by impacts and maybe some of the rocks the mineralogy has changed so that you could generate low molecular weight organic compounds, how would you sample in order to look for signs of life or life that might have organized itself, say, in stromatolite layers on a very small scale? How would you sample and get that chemical gradient in order that solutes moving, cells excreting substances from the small to the large scale across the given sample site?
Wow, that's a big question, so I'll try to snap off one side of it. In my own context as an isotope geochemist and a gas geochemist, around the methane question, one of the things that I emphasize is that the contextual evidence from the other associated gases can be critical. So if we're trying to really understand, even on this planet, the distribution of abiotic methane versus biological methane, two of the really critical aspects to measure are actually, much as I love carbon isotope signatures, what I measure first is the hydrogen and the ethane, because the ratios between those three can be quite illustrative of the origin of the methane. I'll talk more about that at 1:45 this afternoon. But I'm going to pass that on because your question was much more wide-ranging, and there'll be other aspects that the other speakers will hit.
Right. So this gets back at the last question too, is sample selection. And one of the things we do is we start with images to see what we're looking at. We look for things in particular that don't look like they might be physical or abiotic chemical processes. And there's a lot of ambiguity in the morphological signatures. But we start with just standing back and then closer and closer imaging. And both Pixel and Sherlock are going to be really critical to giving us clues to the chemistry. And so we sort of take all the knowledge we have of life on Earth and physical and chemical processes and try to expand that beyond the specific metabolisms to choose something that when we get it back and put it in someone's lab where they have people who can separate out the components and not just burn the organic carbon with the perchlorates, we can actually sort out a lot more what it is. So we basically use all scales of observations and everyone's field techniques to try to get the best sample for analysis, hopefully back into the best labs in the world.
I fear this might be the last question, and I haven't taken any from the left, so from the far left.
Hi, Catherine Majori, McGill University. I believe that you said, Ken, that the focus right now, although is on sample caching and sample return, that might shift to human exploration after Mars 2020. Of course, humans are walking microbial incubators, so once that begins, we will irrevocably contaminate Mars with us. So will there be any kind of shift from searching for extant life and habitability to maybe searching for extant life instead of extinct life?
Well, the question, the real answer to that question is, number one, uncertain, and number two, absolutely above my pay grade. So when I said, I think that we will continue to focus on humans to Mars, that's me thinking that, and I have my own opinions about it. But I think what you mentioned is a definitely worth considering and probably a very good idea to. So we've taken this path toward follow the water. It looked like follow the water to follow the habitability. Look at habitability in a more nuanced way. Mars 2020 now has a much more kind of clear focus on directly looking for evidence of ancient life than the previous missions have, going back to Viking, really, where Viking was looking at extant life. But as you said, we're looking at ancient life.
Yeah.
Do we want to, as a community, and does NASA want to, as an agency, commit to really seriously attacking the question of extant life on Mars before human exploration? It's a critical question to consider. I personally believe we can do both. I think we can, we often say Mars is irrevocably contaminated and all astrobiology is over once humans get there. That's not how I think of it. I think we can do it intelligently and we can do both. And the humans can be enabling, in my view, but that's my view.
Okay, thank you.
Okay, yeah, go.
Okay, I'll keep it short. I'm really glad that you asked this question because this community right here, this is the community that can enable the science of making an extant life search happen. Now, several years ago, some of us, kind of evaluate, well, why would we put a priority on ancient life over extant life? And what it kind of boiled down to was we weren't sure how to do it.
Yeah.
We weren't sure how to do a search for extant life. And it has a lot of different challenges to it, including the technology, the contamination control, and then what biosignatures do you look for, not knowing what the life is going to be. And so I think that we are at that forefront. We're ready to do that extant search, hopefully prior to sending humans. But the how we do it is something that can still take shape, and this community can contribute to that.
Thank you.
Okay, thanks everyone. Great session.